Okay, by my clock, we're good to go. Andrew, you ready?
Yeah.
Kia ora. Hello from New Zealand, everyone. My regrets to not be there to support Andrew, but I appreciate all of you being there in person today. Welcome to Andrew Dunning's master's thesis defense. I have a couple slides I'd like to share with you. It's been quite an adventure. He's been a really fun student, and I think you're going to really enjoy his presentation today. If you're not familiar with the format of a thesis defense here at PSU, Andrew will give a short presentation, about 25-30 minutes, have about 10 to 15 minutes for questions from the public, from the audience. And his committee will reserve questions for after the public portion of the defense. After the defense, we'll give Andrew a little break so you can chat with him in the hallways. He'll have about 5 minutes to get back to his committee. We might give him a little more. And then the committee will question him, and that'll complete his thesis defense. For those of you who aren't aware of Andrew's committee members, I believe we have in the room Ian Maiden, recently retired from Dogami and finding a research home here with us at Portland State. Ian, are you there? Is that a yes? Great. And we also have Martin Streck, a volcanologist in our department, who his students' work and his work have been incredibly helpful for Andrew on this pretty challenging project. Okay, and so with that, I'd like to introduce Andrew. Congratulations, Andrew, you made it to the day. So you may better know Andrew through his Better Geology Twitter handle and YouTube channel. He's a geology enthusiast. Anyone who knows him knows this. He's enthusiastic, excuse me, it's early here, enthusiastic about everything that's interesting, any interesting geology problem that crosses his path. He's kind of like the US Postal Service. He'll work on geology problems outdoors in any type of weather, rain, shine, snow, sleet. Oh, I have photos to show it. So these are pictures of Andrew. He happily volunteered, squeezing into his busy summer last year, sometime in Oklahoma, working in 116-degree weather and 95% humidity. It was pretty hot. And he's having a great time here. Oh no.
Thought it was comfy.
It's freezing for me. Oh shoot. Let me stop share and try this again. Are you still seeing that?
No.
Okay, I'm gonna try this again. Always need some technical difficulty in the morning, or a couple, it seems.
I see your PowerPoint now. Hey.
Okay. Okay, the slides are working. And here he is, looking only a little less enthusiastic, but still pretty excited to be standing at the base of a fault scarp in snowy weather. He worked incredibly hard with all of his field assistants. I know he has some great photos. He has a great project in the Strawberry Mountains that he'll be talking about today. It involved a lot of really hard, rugged work, just accessing the terrain, and also hand excavating his own trench. You can see the methods there, and he's entirely happy in his hole up high in the wilderness. And of course, for those of you who know Andrew, you also know that he's a very talented musician. He plays the clarinet, among many other instruments. And what you may not know is that he's also a world-renowned backcountry percussionist. In all seriousness, Andrew collected, and his field assistants collected over 400 pounds of rock samples and got them out of the backcountry and into the lab so that he can give you this incredible story today. Andrew is a great science communicator, and that's really why I started with the Better Geology bit. He's been interested in communicating complex science topics even prior to his master's degree. He's presented at numerous conferences, professional conferences, and also won a very prestigious award from the Seismological Society of America, a Best Student Presentation Award in 2022. I think that this is an incredible body of work and a great science communicator who's really made a lot out of his master's thesis in his time here at Portland State. I think you're going to enjoy the defense today. And with that, I will stop my share, and Andrew, go ahead and take it away.
One moment, please. Can you hear me on the Zoom?
Yes.
Great. All right, get the show on the road. My project, my master's thesis that I've been working on for just shy of 3 years, title is The Evaluation of the Slit History and Holocene Activity of the Strawberry Fault in Oregon. Or in short, do earthquakes happen on this fault and how often do they happen? Before I get going, I want to pay homage to my grandparents who attended Portland State in the early 1960s. They experienced the 1962 Portland earthquake together back when Smith Student Union Hall was the East Library. And that was, I'm told, a formative part of their early relationship and ergo why I'm alive and here at this school. I just think that's nice. Okay, science, the project. Ian Maiden, who is chilling here in the first row, mapped a whole bunch of previously unknown fault scarps in the Strawberry Mountains 2018-19. This is from LiDAR imaging. So they fly lasers out of the bottom of a plane and the reflections off the ground and the trees and the buildings and the elk, what have you, allows us to map the ground surface and strip all of that extra stuff away. So we just get the surface. And as is often the case here in the Northwest, whenever we collect new data, we find new problems. And this 27-kilometer stretch of fault scarps is one of the more interesting problems I think we've encountered. The Northwest is not an area known for its earthquake activities, but particularly out here in eastern Oregon. The Strawberry Mountains are a sub-range of the Blue Mountains province, which is this. I'll get rid of that. Which is this whole northeast quarter of Oregon. And the yellow lines on this map, which you can see, are quaternary active faults and folds. These are faults that we at least think most of the time are capable of producing earthquakes in today's settings. And there's a conspicuous lack of these here in central northeast Oregon. This mountainous upland, mountains generally are evidence of fault movements, and these are probably no different, but there's very few active faults that we know about, and collecting new LiDAR data, like what was Ian's job for many decades, is integral to our future understanding. Now, the Blue Mountains more broadly are under the influence of this crustal rotation. This is a classic map from 1998 from the esteemed Ray Wells. And the Northwest, broadly speaking, is being swung around violently by the Sierra Nevada block, pushing out the Coast Range block, squishing up the Olympic Mountains and allowing space for the Basement Range to expand laterally. The Blue Mountains, which I've shaded in here, kind of fall into no man's land between all three of these regimes. And a lot of the GPS vectors are really, really slow, so it's hard to divine active tectonics from that alone in this region. But basically, we have compression up here to the north, including the Yakima Folded Thrust Belt, and extension here to the south. This compression is north to south oriented and the extension east to west oriented. The Brothers Fault Zone is included in many more recent models as one of the northern boundaries of this extension. But as we'll see, the fault in question that I've been studying doesn't really conform to that model. The John Day Fault here is almost 100 miles long east to west, and probably has about a 10 million year history of basically every kind of possible fault movement depending on where you are along its length. And that's where the study area is. I'm going to go to this map real quick just to emphasize that Eastern Oregon is really not known for its earthquakes. This is one of the largest low hazard blobs anywhere in the country, or at least west of the Rockies. And generally we think of that as a proxy for low tectonic strain, where the continents we think are not getting squished in an earthquake favorable way in this area. But there's very few earthquakes detected. This is every earthquake detected since 1900 in the Blue Mountains. There's a lot around the edges up here. This is actually a 6.0 major earthquake in 1936. But the Blue Mountains, especially down in the southern part, is really, really quiet. But these new fault scarps that Ian discovered are suggesting that something else is going on. So there's two lineaments of faults that Ian initially mapped. There's this north to south one, the Summit Prairie Fault, and there's this east to west Strawberry Fault. This thing is 27 kilometers long, east to west, includes a number of different strands, and basically forms the range front boundary of the Strawberry Mountains where it meets the John Day Valley. So this main fault we decided was going to be the focus of this work because it's so weirdly oriented. And we have two questions for that. How many earthquakes are represented by these fault scarps? And what is the behavior of this fault through time? Again, there's the John Day Fault, and that shows that the fault scarps I've been mapping generally follow the trace, the interpreted trace of this major fault structure. I don't really have anything to say about that at this time in the presentation other than to say that it will come back. Let's zoom into the study area right here. This is a geologic map that I have been cleaning up and fixing for a long time now. Let's go through this from oldest to youngest. Over here, this is the Canyon Mountain Complex. This is the Permian era bunch of ocean floor ophiolite complex that was folded and squeezed and thrust up 7,000 feet into the air. So this is 300 million years old roundabout. Then there's this little fault here, and these rocks are somewhere in the neighborhood of 20 million years old. And on top of those, this pink unit, the Strawberry Volcanics, are the dominant surface bedrock we find in this study area. This is a suite of largely bland gray lava flows that stack on top of each other beautifully that sort of date 17 to 12 million years ago. It also includes one of the largest rhyolitic eruptive centers in North America, which is neat. But these fault scarps, which are traced here in red, are also clearly tracing these older bedrock faults that are delineating the boundaries between older John Day rocks and younger Strawberry Volcanics, apart from over here, but this is a weird area. The fault also crosses glacial drift units of 3 different ages. We have this really old age moraine here. This is a glacial deposit. Then there's this middle-aged one here. This is just gorgeous moraine morphology over here. We think this is probably last glacial. And then there's this third, very young glacial advance, which is down here in the bottoms of all of these canyons. The Canyon Mountain Complex, as a giant block of ocean crust, is really solid and is probably acting as a west end boundary of rupture on this structure. But the rest of it is generally free to fault at will, as far as I can tell. So to summarize the geology, the Holocene surface ruptures of the Strawberry Fault are generally following the John Day Fault's trace. The planar lava flows of the Strawberry Mountains are tilted south 10 to 20 degrees like this. The John Day Fault is one of the structures that originally contributed to the uplift of the mountains and the downdropping of the valley, probably in Miocene time, 3 to 5 million years ago, depending on whose paper you read. But anyway, the summary is that these fault scarps are probably representing reactivation on this pre-existing structure. I've been using the word scarps a lot, and since there's a lot of non-geologists here, I just thought I'd point out what a scarp is. So before the earthquake, if you assume a flat surface, like erosion has come and smoothed out the surface over time, then after an earthquake, you have this face right along the fault plane. This is called a scarp. And then over time, that scarp collapses and you get what's called a colluvial wedge out in front, and the top of the fault sort of erodes and lays back. And it looks like this. This is a pretty crispy scarp. This is morphologically quite young compared to a lot of the other ones we see in Oregon, especially here on the west side because it's so rainy over here. But it's dry enough that this fault scarp, however old it is well preserved in this terrain. An analysis of the fault strands show that it's a normal fault, which means it has vertical movement. There's no lateral movement at all that I've been able to find anywhere in this fault system. Average dip is about 45 degrees to the north, or 54, so that's about like that. 27 kilometers of youthful fault scarps, and these fault scarps are ranging from 0.75 to 5 meters generally. There are less young, much more eroded scarps that range up to 19.7 meters in glacial terrain. And I found a couple of 50-meter offsets in the bedrock areas. This is what the scarp looks like at one of my favorite sites up in Onion Creek. And this is looking south, so the mountains in an earthquake go up, and this basin where Kira is standing goes down. This plot here shows a series of the offsets, the vertical separations across the fault along the length of the best preserved scarps, which is over here. And the offset shows variability with surface age. There's sort of a cluster down here in the 1 to 1.5 meter range. And based on a fault of this length, that's about the rupture height vertical separation you would expect from Wisnowski and others who have done all sorts of fancy statistical analyses. So we can assume that everything above roughly that level reflects multiple events. But it actually looks like this. This is the cluster of younger youthful scarps, 1, 2, 3 events maybe. And then there's all of these up here, which reflect far, far longer activity on this fault. The western half of the fault here has a lot, generally larger, higher offsets, more diverse. They're facing different directions. They're well developed. In the eastern half, these scarps are smaller, more sinuous, and generally less well preserved. Take that to mean that this west half of the fault has probably seen longer activity, and this east fault is still in the process of establishing itself as a permanent structure. This is what one of these scarps looks like in the field. This is my favorite one. This is on top of the Graham Creek Glacial Moraine. So this is last glacial maximum aged glacial deposits. We've got my field assistant, Kate, down here. This scarp is 2 Kates tall, roughly. It's about 2.4 meters, and here's Ashley on top to round out that scale. This is a big structure. It's a big surface, but without the LiDAR, I would have walked right past this. This is a really dense, really thick old growth conifer forest, and tools like this LiDAR really bring these structures, these fault scarps to life. So the Strawberry Fault offsets till from 3 glacial advances. We have old glacial advance here. This is that 19.7 meter offset. We're assuming that's definitely pre-last glacial maximum. In this QGM, we're thinking that's last glacial maximum, 2 to 3.3 meters in most places. And over here, a short length of this fault faces uphill, and that causes the slope to form a little dam here and allows all of this alluvium and sediment to accumulate behind it. But for these other two, the fact that they're in glacial terrain means we can date the features to find out how long these have been offset. We can use cosmogenic radionuclide dating to constrain these slip rates. Oh, and there's 2 Kates again for scale. I forgot I put that in there. The glaciology, the glacial morphology of the Strawberry Mountains is beautiful. It was very heavily glaciated in past ice ages, and in my opinion, contains some of the best glacial morphology in Oregon. Previous studies on the glaciation in the Strawberry Mountains didn't do any kind of absolute age dating of features. They walked through the woods and counted boulders and dug pits. And that's an impressive amount of work. And generally the things they said have correlated with what I've found with my analyses. But these previous studies did not have the LiDAR. They relied on air photos and dead reckoning to do their research, which is impressive. I have it a lot easier nowadays. But the main way to date these features is through cosmogenic radionuclide dating, is with a fun little isotope called helium-3. So as a boulder, excuse me, as this glacier bulldozes its way out of the mountains, it drops all sorts of stuff along its edges, and including boulders the size of cars usually. And the longer that boulder sits there, the more cosmic rays are impacting lithium atoms trapped in pyroxene, and the more helium-3 is mechanically beaten off of those lithium nuclei. So helium-3 is also formed by radioactive decay of things like uranium and potassium, but mostly here we're looking at spallation from cosmic rays. That's galactic protons is the magnificent phrase I was given for that. So the helium-3, after getting knocked off of the lithium atoms, gets trapped in the crystal structure of this pyroxene, and that allows us to count it. We know roughly the age of most of the Strawberry volcanics, so we can have a good guess to estimate the ratio of radiogenic to cosmogenic helium-3, and it's not terrible. It might be as much as 20%, but the calibration of those numbers is something I'm still working on. There's basically no absolute dating for glacial features in Eastern Oregon, except for a couple of spots in the Wallowa Mountains and in the Steens Mountain. So these are really data that is filling in a hole in knowledge of glacial chronologies in Eastern Oregon. But we're using this isotope specifically because this is all mafic terrain, it's all basalt and andesite. The more common method, beryllium-10 dating, relies on quartz, and I really only saw 2 rocks that contained quartz in the entire project. But we managed to sample from 3 moraines, which matched our interpretations of the morphology we saw in LiDAR. So we assumed those to be old pre-last glacial maximum, last glacial maximum, and younger post-glacial maximum drift units. Some of the boulders on these moraines look like this. They're well exposed. They've clearly been sitting there for a while, haven't moved, easy to sample. Other ones are like this one, which is buried almost all the way up to its top and was very stubborn to get out with a chisel. So was this one. That's Kira here, kicking it on this big boulder. A lot of the boulders on this particular moraine were covered in this knee to hip deep snow brush, which was basically like wading through mud that scraped you. Terrible. But anyway, we packed out about 400 pounds of rock out of the wilderness over 2 weeks. That took a lot of work, a lot of heavy packs, and my mom actually came out to help us pack some of these rocks out one day. Thanks, Mom. These are the moraines we sampled. We basically tried to get as good of a spread we could along the length of the top of this moraine, where boulders are big enough that they haven't been rolling around. If they're still on top, it probably hasn't moved very far at all. We did this moraine down here. We thought before the ages came back that this was a post-glacial maximum moraine. This is that really tall, really old one. It's very quite rounded. For comparison, the crest of this moraine here is about 1 meter wide, whereas on this one, it's closer to or exceeding 10 meters in width. So this has been sitting here eroding for a lot longer. And this is that gorgeous last glacial maximum set of moraines. So the ways that they appear differently in the LiDAR are what allowed us to come up with these age estimates, and also using that previous research. Turns out they were dead on in most everything. So we dated these moraines using the weathering rinds of these boulders, which got sampled, crushed, and the pyroxene crystals were separated. And that looks like this when it's all said and done. This one yielded next to nothing, but this one filled up 2 vials. So there's a lot of variability when you're doing boulder sampling with such a wide range of rocks, because we've got 5 million years worth of lava flows that these boulders are sourced from and that we're trying to sample. The helium-3 ages are affected by things like snow cover and that non-cosmogenic helium, but the ages presented right there are not calibrated for any of those except for snow cover. But we constrained their age with a bulk sample that I pulled from about 1.5 meters under the surface. So that's mostly shielded from incoming cosmic rays. And because it's shielded, it probably reflects the average bulk background helium-3 of the source area. That's an assumption, kind of a big assumption, but we take what we get when data is limited. So the numbers we get, that beautiful Graham Creek moraine, 23,267 plus or minus 586. That's a really nice, comfortable margin of error on that one. I'm very pleased with this age. The next one behaved less nicely, a little wider range, 24.2 thousand, 5,000 year margin of error on that one. But then this older one, this big granddaddy, 111,670 plus minus 13,000 years before present. This is a time in history called marine isotope stage 5D, which is one of the earlier large glaciations in geologically more recent time, as far as I understand it to be. I'm not an isotope geochemist. So at these last glacial maximum sites, these ages, by the way, correlate perfectly when you account for the inherited helium. They match perfectly with the glacial ages from Steens Mountain and the Wallowas. So this fits right in with the chronology that we do know for Eastern Oregon. But this scarp here, 2.4 meters high over 23,000 years, you can average that out to a slip rate per year. And that's 0.11 plus minus 0.02 millimeters per year since the last glacial maximum. A 2.4 meter offset is 2, maybe 3 earthquakes over time, but there's variability in the time between earthquakes, and as in any natural system. So this older, taller moraine here with the 19.7 meter scarp allows us to peer deeper into history and get a sense for that slip rate over deeper time. After a little Monte Carlo statistical analysis, we get 0.18 millimeters per year, and that covers many earthquake cycles, at least 9, maybe more than 10. But this is a slip rate that is not fast, but it's not slow, and it's about right for where it's located on the continent, far away from the continental margin, but also in an area that is experiencing tectonic forces. So how many earthquakes are recorded on the Strawberry Fault? This is that Onion Creek site I briefly mentioned earlier. The scarp faces uphill in this area and impounds this small dammed sedimentary basin that's about 135 by 40 meters, about the size of a soccer field when it's all said and done. These contours are 1 meter apart. So this is really strikingly flat right here. Hiking up this very, very steep terrain, this trail climbs 1,200 feet in about a mile, which we then carried all of the shovels and augers and buckets and water jugs up repeatedly. But the scarp at this site is 1.6 meters tall, and it's offsetting what we're assuming to be this last glacial maximum glacial till. And then you cross the scarp and you're in this lovely flat basin. Nice place to have a lunch break or dig a trench. So that's where we did our auger transect, in this basin full of sediments that go back at least since the last glacial maximum. We did 17 of these cores and that trench, which I'll get to later, and that revealed 5 distinct soil lithologies. We have the glacial till down here at the bottom. You'll note it has some angular rocks in it. It is contaminated from the overlying units. It's actually much lighter when it's in situ. Above that, we have a buried soil unit. That's this really dark, silty clay, clayey silt, of course, the difference is important, unit here. This is as much as a meter deep, actually in some places more than a meter deep. But then on top of that, we have 10 to 20 centimeters of Mazama ash, which is from the eruption of Crater Lake. And we know exactly how old that is, 7,760 plus or minus a few years. So this is a beautiful age marker to have in this sedimentary sequence. On top of that, there's apparently a long period of just continued normal alluvial fill into this basin that includes pieces of the Mazama ash all throughout the soil column. Until that is, we get to this unit E, which is the modern uppermost soil unit at this site. This includes your active root mats, and it's all full of organics and stuff. But in this core, there's actually a couple of little tiny granule rocks in here, which you don't see anywhere else in this unit until you get to the glacial deposit down here at the bottom. Fortunately, we were able to get carbon-14 with charcoal for all of these soil units, so we were able to carbon date effectively the time period that these sedimentary units span. This is what these charcoals look like. These are, I cherry-picked the 2 largest ones, of course, but these are millimeter markers. And even though these are hundreds, and a couple of them are thousands of years old, you can still see growth rings on these pieces of charcoal that have been buried for who knows how long. I love that. So this is what our auger transect revealed. This is 5-to-1 vertical exaggeration, by the way. Bottom to top, same sort of way. We got this glacial till more or less in situ. Sometime between the last glacial maximum and 7,000 years when the Mazama ash was erupted, we have an earthquake. The first earthquake on this site created at least a meter, probably closer to 1.2 meters of accommodation space that this dark soil was allowed to fill in, and it was impounded by the fault. And we got the 10 to 20 centimeters of Mazama ash, and this alluvial unit that contains the Mazama ash, if you use your imagination and back it down a little ways, you can see how it was probably perfectly flat before the last earthquake, or nearly flat. It was, of course, faulted during the last earthquake. The glacial till up here was thrust up and created that vertical scarp face that I pointed out earlier. And cobbles and clasts and rocks were raveled off of that steep face and went all the way out to core 13, on top of the rest of the soil units, which do not contain any rocks at all. So this is a good indicator for what we call the most recent event horizon. It's at this level in the soil that the most recent earthquake on this fault probably happened. At this whole site, from the auger cores, from the glacial till on the upthrown side to the glacial till on the downthrown side, it's about 3.3 meters of offset, which matches the other offsets we see on last glacial maximum age deposits. We dug a test trench with lovely, wonderful help from the Geological Society of the Oregon Country field trip volunteers that came out and helped dig this trench for the first time. Of course, we came right on down on top of a boulder that was sitting on top of the fault plane. So that complicated the stratigraphy really annoyingly, but the contact between the ash and the dark buried soil is this clean all the way in the trench. This is what that looks like when I take 400 pictures and stitch them all together in a 3D modeling software. You can see everything, no? No? Oh, okay. There's the interpreted log. We've got the in situ glacial till here. This is that buried soil unit. Mazama ash is draped, folded, and fractured where it passes over the top of the boulder. And we have a little bit of it up here. So just in the trench alone, we have 0.7 meters of vertical offset. And then when you project that down to the rest of the auger transect, it ends up being about 1.2 meters of vertical separation during the last earthquake on the Strawberry Fault. These blue units in here are units that I'm interpreting as filling in these gaps, shortly following the last earthquake on the site, because the Mazama ash is separated and the gap between them is filled with this really light, fluffy sediment that includes rocks and pieces of ash and all sorts of other messy things that are hard to figure out. But generally, this most recent earthquake event horizon, which is the top of this ashy alluvium blue unit, generally that held out all the way through. So here's the order of events once again. Glacial till was here before, then sometime there's an earthquake and we get infill down here of the buried soil. Then the Mazama ash was dropped down on top of that. 10 centimeters, in some places up in the trench, it was up to 25 centimeters deep. So that was probably the lowest point of the basin at that time. Then we have that ashy alluvium fill. And then we have the most recent earthquake. And since the most recent earthquake, we've had about 30 to 50 centimeters of soil growth and building just from forest leaf litter and whatever other processes build soil in forests. I don't know, Scott, maybe you can tell me later. So we get that's wrong. Most recent earthquake is supposed to be 1.2 meters of separation on the Mazama ash. So that's our idea for how this site worked. We collected charcoal, as I said, from every one of these soil units, which allows them to get carbon dated and allows us to estimate the ages of each soil unit. So penultimate earthquake, not a great margin of error, roughly 16,000 years. I would like that to be smaller, but beggars can't be choosers. We did get some charcoal ages from that buried soil ending about 8733 years before present. Mazama ash, we know exactly how old that is. The next unit up, the ashy alluvium, was full of charcoal. This was a lot of fun to sift through. And then the most recent youngest soil unit was as well. And that gave us a most recent earthquake age of 1278 to 1094 years before present, or CE 672 to 857, when the hip new invention was Greek fire. So to review, to summarize, to pull this all back to the fundamental tectonic quandary that this fault presents, we do have evidence of consistent slip on the Strawberry Fault through the Quaternary at least 100,000 years, maybe as far back as 300,000 years if you include those bedrock offsets I mentioned. There's an antithetic fault which meets it at an angle. It's parallel, but it dips the other direction, so they intersect at depth. And that gives a primary stress for the tectonics driving movement on this fault at 350 degrees azimuth, which is this direction. A fault like the John Day Fault can reactivate within generally about 60 degrees of its orientation. Strawberry Fault scarps don't really fit that. This is a more elegant diagram by Tom Broker and others from a few years ago, showing broad extension of the American West. How do I summarize this in 2 sentences? Well, I mentioned the crustal rotation earlier, where the Sierra Nevada block is driving rotation of the Coast Range, and that allows extension everywhere between the Cascade Mountains and the Rocky Mountains up here in Montana. All through here, we have sets of parallel normal faults, which demonstrate extension across geologic space and time. The geodetic timescale, again, for this area is really too short to show clear, definite driving forces, unlike on the Coast Range or down in California. But the arrows, the primary stress on this fault, even if I adjust it to fit the John Day Fault's bedrock trend, it barely fits if you use your imagination, but still this direction is not parallel to the basin and range extension. It's in fact parallel with the driving forces of the compressional fold and thrust belt. So this is all compressing up here, but this is moving in the same direction. It's moving in the same azimuth. It's stretching instead of squishing though. So that's a head scratcher. I like the way that Tom Broker explained the whole middle part of this diagram. It just said distributed, normal, and strike slip faulting. Seems to be the case. This fault isn't really helping answer any of those tectonic questions, but it does raise flags. There are more faults in this area. Up here in the Unity Basin are actually probably the most similar. Ukiah Basin, excuse me. They trend roughly a similar direction and have the same magnitude of offset. But it's weird, and I love that it's weird. So to summarize, the Strawberry Fault is a quaternary reactivation of this Miocene John Day Fault structure. There are at least 2 major earthquakes since the last glacial maximum. Empirical scaling relationships, which are statistical models of previous known recorded earthquakes, suggest a fault with this length and this vertical separation is probably about a magnitude 6.7. That's the size of the Northridge earthquake in 1994. So that's a significant shaker. Most recent earthquake was in the 8th century CE, and the Blue Mountains province is clearly something different from our models is going on there, and it deserves attention for both seismic hazard analysis and fun tectonic modeling. Science is not something you can do by yourself, and this project has been helped by so many people. PSU obviously has been good. Malheur National Forest was awesome. Hannah Grist is the geologist on staff at the National Forest. She was amazing. She got this trench. She just said, you can do it. It was amazing. Other trenches I've worked on have taken years in permitting. Mine, I just emailed them and it was good to go. So that's great. Geological Society of America gave me money. So did the Mazamas, the Central Oregon Geoscience Society, and the Scion Natural Science Association. Thank you all to those organizations for your support. But for me, it's all about the people. I had Kate was the first field assistant I had. She was amazing. Then I had Kira and Lycan. Kira flew out from Vermont, from Middlebury College, to collect rocks with me, which I then sent back with her on the plane so she could crush and pour hydrofluoric acid on them and separate out the crystals for me. She sent those crystals down to Greg Balco in Berkeley, California, who gave me the helium concentrations and the age data for the boulders I sampled. They were tremendously helpful. Lycan is a prolific cook. He is amazing at field meals. They got Heather and Zoe helped me out. GSOC, I cannot remember this gentleman's name, dug most of the hole by himself before I got in there. And the elusive, difficult to photograph Annika Walter also helped out. And so did my buddy Riley, who's back up there. And scientific collaborators are the most interesting for me. Ashley Strike, of course, thesis advisor, Will Amadon and Greg Balco are basically the crown princes of helium-3 dating in North America. Martin Streck for both advice and his previous very high-quality work in the area. And Ian Maiden, committee member, Ray Wells, Scott Bennett, Richard Stryon, Andrew Miggs, Laura Walkup, Willie Scott, all tremendously helpful and supportive of this project. That's all I've got. Thank you very much for listening.
Thank you, Andrew. We have time for some questions.
Anything at all?
I probably just don't know because it's not my field. You probably said it, but those 2 earthquakes that you identified, do you know what magnitude they were?
Probably about 6.7.
Both of them?
Probably. I mean, the offsets on the eastern half of the fault are less well preserved, but they do match that same sort of 2 earthquakes at about 1.2, 1.3 meters. So it ruptured at least that whole 27-kilometer length at least twice. John?
So yeah, you talk about quaternary offset, so more recent offset, you have some offset rates really because you have distance and time. You also talk about this fault being active this far back as the Miocene, correct?
The John Day fault was. I'm not prepared to make that leap for this structure.
I'm wondering do you have a sense of what the total offset would be over the entire time that this fault system, let's say, that has been active?
So I don't know what rocks are underneath the valley gravel fill in the John Day Valley. Well logs just say basalt, so I assume it's some kind of volcanic rock. If you assume that's the same, if you assume that's the same rock as on top of Strawberry Mountain, just a couple miles away, total vertical separation is about 6,000 feet, which is a lot. Yeah, Jim?
So you there's sort of 3 distinct morphologic facial moraines there, but your 2 youngest ones kind of have the same.
Yeah, yes, they did. This little one.
Andrew, could you repeat the question?
Oh yeah, Jim's question was the 2 younger moraines. What was the question, Jim?
You had these 3 distinct moraines, and the 2 younger ones had 3 moraines.
Yes. So this one here, yeah. So Jim is asking, these 2 moraines had very similar age ranges, but the morphology is pretty different between them. I think this one has seen substantial modification by the streams that are on both sides of it that are eroding the bases of it. It's got this kind of weird saddle shape to it. This is the highest point of the moraine, and this is the lowest point right over here. So that was confusing. A lot of the boulders were in lines, in rows. It looked like it was really young. And this moraine is flanked in, let me pull up Ian's perspective image. Oops. Not that one. It's flanked in lateral moraines. This one right here is beautiful. That right here is a boulder the size of a Volkswagen Bug. I didn't date it because it was rhyolite, and it was the only rhyolite boulder I found in the whole project. It would have been the most helpful one, but I couldn't date it.
So maybe the range you were dating related were sort of 2 age categories, one had been eroded.
That's my understanding. That's yeah. The structure up here also, the morphology is bizarre. I took one sample up here. I can't remember what it gave back, but I couldn't really figure it out, so I didn't sample it.
So more generally, if there are indeed I think the last fish class the other ones are both older than that, or you think there is actually something younger than
In this area, and in the Rocky Mountains, which is where I did a lot of other reading, and in the Wallowa. So the question was, how young do I think the younger one might be, basically? Research up in the Wallowas at Wallowa Lake, McCarty and others, showed a small push about 17.2 thousand. That's a little before younger Dryas, but it's probably in that neighborhood. I'd like to go back out and sample some more of these lateral moraines if anyone has any spare grant money laying around.
Online question.
Online question.
So hopefully I can say this loud enough. So what is Austin Gillum online? that's
Oh, hey,
asking,
Austin.
what role do you think the Paleozoic metasedimentary rocks in the area have in explaining the apparent extension in an otherwise compressional setting?
I have no idea. What role do I think the sedimentary rocks in the area? Yeah, Canyon Mountain Complex has a complex deformational history. It's got at least 2 compressional events from the papers I've read, and that does not include the more recent uplift. I know it's solid enough that younger scarps either are not preserved or are not capable of rupturing through those rocks. I think there's probably more fault scarps further west in the Aldrich mountain range, which is the next mountain range to the west. Same structural trend, but I haven't been out there yet. I can speculate wildly and suggest that maybe there's a boundary of one of these basement terrains in that area, because there's 3 or 4 of them. Maybe there's a terrain boundary in this area that is affecting the way tectonic strain is expressed on the surface. Is that a fair, wild speculation, Ray?
Yeah, inheritance of older structures can affect the way young deformation. If they're proceeding for a long time, you might expect normal fault to invert.
Mhm.
Turn around and go the other direction.
Yeah.
Are there any, if I could follow up with a question, are there any earthquake focal mechanisms in that area? I showed some earthquakes.
Yeah.
There are actually focal mechanisms that can help you tell what the stress orientation.
Most of them were really small, like
There are
magnitude
also
1.
Maybe some
Where is that?
few hydrocarbon wildcat wells somewhere. Wells with
None that were that deep
borehole
in
breakouts.
where I looked.
So you can get some idea of the
I know this.
temporary stress orientation.
So Ray Wells was asking about stress orientation in earthquake focal mechanisms and in borehole breakouts. I have not found borehole breakout measurements. There was a tiny little, earthquake swarm just east of the Summit Prairie Fault area in the Monument Rock Wilderness. And these are mostly normal basin and range style focal mechanisms. A lot of these smaller ones are all over the map though. And these are mostly magnitude 1 to 2. It's hard to say. I will look for borehole breakouts though. It's a good idea. Yeah, Scott.
On the, great talk by the way, Andrew.
Thank you.
On the broker model,
Yeah.
if they pull that map up. You know, I think, in fact,
Oops, that's old.
dashed blue lines that form arcs across the map,
Yes.
you know, those are small circles around a rotation pole. You know, and if you were to draw smaller radius arcs closer to the field area, would the Strawberry Mountain Fault be sub-parallel to those arcs? And would you then expect the Strawberry Mountain, its orientation, you got it drawn there, right? That short little red line, right? Wouldn't that be sub-parallel to these arced with dashed lines? And why would you not expect strike slip fault motion?
Well, I did expect strike slip motion.
Okay.
It wasn't there based on what I found. It's possible that the John Day Fault is doing that at depth and it's just been buried, or is expressing itself weirdly at the surface, like in some of the faults in Death Valley kind of do that. I have not thought about doing any circles from these pole points. Looks like the Brothers Fault Zone pole point follows that nicely.
Yeah, right.
Silesia, Coast Range, maybe. It's a good idea. I'll look into that.
Great. Thanks, Andrew.
Yeah, Percy.
Hey, nice talk.
Thank you.
Did you see any paleosols in your trench?
Just the buried units. Nothing was, I mean, I wouldn't call a 20,000-year-old soil paleosol, but
Why not?
because I worked in the John Day fossil beds, and those are 20 to 30 million years old. Okay, I saw a paleosol.
Why couldn't you date that rhyolite folder that you pointed out?
Because that means I would have had to find more money in another lab and a different field assistant, and doing all that for one boulder is impractical. Maybe I'll find more in the future. I do have a sample of it in the basement. So if that comes up, I could.
Is it rhyolite has to be dated with some different method?
Yeah, the beryllium-10, which is the standard method most people use in most settings, uses quartz. Basalt and andesite don't have any quartz in them usually. Rhyolite usually does. This boulder had a lot of quartz in it. So in the future, if I get money for dating quartz, I will date that boulder.
Okay, oh, one more.
One more from Scott.
So I was curious about the John Day fault. The previous map had it kind of had a 90-degree bend.
Yeah.
Pointed out, it kind of shoots off to the south. I wonder if you could talk about what you think, how that other fault trace that comes in from the south, how that interacts either kinematically with the east-west fault that you focused on, and if it has any role with, say, the slip distribution that you were tracking, or how do those faults interact? What are your thoughts on that?
So this is a rather inelegant diagram I made when I was putting this presentation together a couple weeks ago to help me try and visualize broadly what's going on. It didn't help that much, but there are a lot of faults, including some of the younger active ones that Ian has found in the LiDAR right here, just south of it, indicating east to west, almost due east to west extension right here. I could be convinced that the Strawberry Aldrich Mountains are being pushed to the west very slowly, and maybe that is exploiting different faults or fractures nearer the surface in a way that is counterintuitive.
And where does it, how does it affect your slip distribution? You have a nice slip distribution plot, right?
Yeah.
Can you show that? Maybe discuss on how, where that fault comes in, and if you see any effects on those data.
So all of these are on or very close to that mapped John Day fault trace. These are where there's large structural offsets. And then here on the west, this part of the fault goes right up the top of a ridge, a really narrow ridge, a really sharp ridge. So the rupture is not going in a place where I would expect long-lived faulting to occur. So I think this is propagation probably. It's possible that before this propagated that there were other earthquakes that ruptured north of the Canyon Mountain complex heading toward the west. I know Ian has mapped some scarps over there. I didn't get anything useful out of them from topo profiles. They're just not very well preserved.
Does that north-south fault come in somewhere on this diagram? This is an east-west.
Andrew, can you go back one slide? Can we see that north-south fault on the smaller? Yeah.
So the John Day fault swings around and goes down this way. This is the John Day River. The geologists that interpreted that bend, I don't know why they call it the same structure. For a lot of the length, they call the John Day fault a major strike slip reverse fault. There's no morphology that suggests it's doing that right now, in my opinion. But I think it is bolstered by that north to south fault by Summit Prairie down here. It's very confusing and interesting, and I really want to get back out there.
Sorry, Andrew, I'm going to elaborate on Scott's question. So as you move east of where that north-south fault projects towards the Strawberry Mountain Fault, what do you notice about scarp heights moving east from that point on?
These
Are
scarp
they
heights,
just as high or are they lower?
they're just as high in this sort of most recent few events, but there is very little in the longer term, bigger.
Right, so go to the next slide, slide 14.
Sorry, slide 14.
Go down one more slide. Yeah.
Ah, yeah.
Okay,
That north-south fault comes in right about here.
right. Good questions.
You're welcome. Austin says more things. Put the sense of motion on the boundary fault between the Canyon Mountain Complex and the Strawberry Volcanics. That's this one right here. It's called the Indian Creek Fault, you're right. That's a normal fault. The John Day, Clarno Group, and Strawberry Volcanics are down thrown relative to the Canyon Mountain Complex. There's a big stack of lava between the high points of here and Strawberry Peak.
Okay. And with that, it is 9 a.m. or close to that. Thank you, Andrew. If we could get one more round of applause for great defense. I plan to purchase some pints in Andrew's honor when I return. So mid-June, just approaching graduation. Try to get into our little email chain, and it'd be great to have you there to celebrate with us. I'm sure he has some plans for today as well. Andrew, fantastic job. Why don't you take, let's say, 5 minutes and come on back to me, Ian, and Martin. Thank you, everybody, for your attendance today and your wonderful questions.